Advanced GraphRAG and Knowledge Agents, let's dig in. Before we build a single knowledge graph, we need to understand the problem we're actually solving. Standard vector-based retrieval is everywhere, and it's genuinely great, until it quietly isn't. This module is the honest origin story of why graph-based retrieval had to be invented. Quick refresher, plain English. Retrieval augmented generation means, before the language model answers, we go fetch the most relevant pieces of your documents and hand them over as context. The model doesn't have to memorize your data, it reads the right page just in time. Here's how the classic version actually works, step by step. We chop documents into chunks, turn each chunk into a vector, a long list of numbers that captures its meaning, and store them. At query time, we embed your question the same way and pull back the chunks whose vectors sit closest. Watch it flow. The intuition behind embeddings is lovely. Every chunk becomes a point in a high-dimensional space, and texts that mean similar things land near each other. Ask a question and you grab the nearest neighbors. It's like a library where books about the same topic magically shelve themselves together. And to be fair, vector RAG earned its popularity. Lookups are blazing fast, millisecond approximate nearest neighbor search across millions of chunks. It's plug and play, it scales without breaking a sweat, and it copes gracefully with messy, unstructured text. For a huge class of questions, it's exactly right. Under the hood, the match is just math, cosine similarity between the query vector and each chunk vector. Here's the whole idea in a few lines of Python. Notice there's no notion of relationships here, only how close 2 points are. Hold that thought because it's the crack the whole module pours into. So here's the core limitation stated cleanly. A dense embedding represents a chunk as an isolated point. Two facts can be deeply connected, cause and effect, parent and child, step 1 and step 5, yet sit far apart in the space. Vectors capture topical similarity, not explicit relationships. From that one constraint, 3 classic failure modes fall out, and they're the spine of this entire module. Multi-hop questions, evidence scattered across non-contiguous documents, and global summarization over a whole corpus. Let's take them one at a time with examples you'll actually recognize. First failure, multi-hop reasoning. Imagine asking, which market condition affects the executive who owns our biggest revenue line? Answering that means hopping executive to financial metric, to market condition, 3 connected steps. Vector search grabs chunks that look like the question, but it has no way to walk that chain. Now picture the same question on a graph. Each entity is a node, each relationship is an explicit typed edge. Answering becomes a walk, start at the executive, follow owns to the metric, follow affected by to the condition. The path itself is the answer, and you can see every step. The reason is structural, not a tuning problem. Each hop depends on a relationship that lives between chunks, not inside any one of them. As you add hops and entities, vector accuracy doesn't gently dip. It degrades monotonically, and on multi-entity enterprise queries it can collapse towards 0. No amount of bigger K saves you. Second failure, non-contiguous documents. Real answers are often spread across many pages and files. Chunking, the very thing that makes vector RAG work, slices the narrative thread that made those relationships legible. The clue in chunk 3 and the payoff in chunk 90 never meet. Let's make that concrete. On the left, a connected passage where a cause links directly to its effect. On the right, after chunking, those two halves land in different boxes with no edge between them. The information still exists, but the relationship that made it useful has quietly evaporated. It gets more fragile. Vector RAG is notoriously sensitive to chunk size, overlap, embedding model, and your retrieval K. Change one and your answers shift. That sensitivity is a symptom of the real disease. We're approximating relationships with proximity, and tuning knobs can't conjure a relationship that was never stored. Third failure, and it's a sneaky one. Ask what are the main themes across this entire dataset. There's no single chunk that answers that. It's a query-focused summarization task, not a retrieval task. Vector search fetches a handful of similar chunks and confidently misses the forest for a few trees. It helps to name the mismatch. Retrieval finds the needle. Summarization describes the whole haystack. Global questions are inherently about the haystack, its themes, its structure, its shape. A tool built to find needles will always answer the wrong question, no matter how good its needles are. So that's the RAG bottleneck in one sentence. Flat vector retrieval stores meaning but throws away structure. Multi-hop, scattered evidence, and global themes all fail for the same root reason. The explicit relationships between facts were never captured in the first place. Now for the good part, the fix. The fix is to stop pretending text is a bag of points and start treating it as a network. A knowledge graph models your data as nodes and edges, entities, and the explicit, typed relationships between them. Formally, a graph G is a set of vertices V and edges E. Simple idea, enormous consequences. Let's ground it. Nodes are the things you care about: people, organizations, dates, products, concepts. Edges are how they relate, owns, reports to, affected by. And both can carry properties, little key-value facts attached to them. Now relationships aren't approximated by distance, they're first-class, stored, and queryable. So how does unstructured text become this network? At a high level, we read the documents, pull out the entities, and extract the relationships between them, wiring up nodes and edges as we go. We'll spend all of Module 2 on the how, different construction methodologies with real trade-offs. For now, just hold the picture. Here's the pivotal shift. In vector RAG, retrieval is a similarity lookup. In GraphRAG, retrieval becomes traversal. You start at relevant nodes and walk the edges to gather connected context. Instead of grabbing whatever looks similar, you follow the actual relationships, which is exactly what those hard questions demanded. Graph traversal gives you two dials vector search simply doesn't have. Depth, how many hops you follow outward, say 1 to 20. And breadth, how widely you fan out to adjacent relationships at each step. Tune depth for deep reasoning chains, tune breadth for comprehensive overviews. You're navigating, not guessing. And because relationships are stored explicitly, you can ask for a path directly. Here's a tiny taste of Cypher, Neo4j's query language. We match an executive, follow 1 to 3 relationship hops, and return the market conditions at the end. We'll go deep on this in later modules. Today, just feel how natural a multi-hop query becomes. Let's anchor this with a real comparison from Neo4j. They asked which market conditions impact Apple's Mac product line. Vector search returned 3 broad factors, basically foreign exchange, supply, and the macroeconomy. Graph search, walking the relationships, surfaced 24 distinct conditions. Same corpus, wildly different completeness. That gap isn't a fluke, it's the whole point. The vector system wasn't wrong about its 3 factors. It just couldn't see the other 21 because the connections to them were never stored. Graph traversal reaches them deterministically. Completeness stops depending on whether the right chunk happened to be similar. Now let's map graphs back onto our 3 failures. Multi-hop solved because the chain of relationships is exactly what we traverse. Executive to metric to condition, that's a path and the path is the answer. The question that broke vector search is the question graphs were born to answer. Non-contiguous evidence also solved. When the cause in document 3 and the effect in document 90 are linked by an explicit edge, it doesn't matter how far apart their text lives. The graph reconnects what chunking severed. Distance in the document stops mattering, the relationship is what we follow. Global summarization solved differently, and this is a sneak peek at Module 3. The graph is partitioned into communities, clusters of tightly related entities, and each community gets a pre-written summary. Answering a global question becomes a MapReduce over those summaries, instead of a hopeless scan of every chunk. There's a bonus benefit that auditors and doctors and lawyers adore: explainability. A graph answer comes with its path. You can see exactly which entities and relationships produced it. Vector similarity says, trust me, the math agrees. A traversal says, here's the trail. That traceability is gold in high-stakes domains. And explicit relationships do something quietly powerful. They reduce hallucinations. When the model is handed structured, connected context instead of a few loosely similar snippets, it has less room to invent the glue between facts. The graph supplies the real connective tissue, so the model doesn't have to guess it. Now, honesty time, graphs aren't magic. There's an upfront cost. You have to design a schema and build the graph. There's ongoing curation as data changes. Traversal is heavier than a millisecond vector lookup, and very dense graphs bring their own scaling headaches. Powerful yes, effortless no. Which means the real answer to vector versus graph is, it depends on the question. Vectors shine for fast, single-fact, fuzzy recall tasks, search, support, chatbots. Graphs shine where relationships, multi-hop reasoning, and explainability matter. Medicine, law, finance, research. Match the tool to the shape of the question. And in production, the grown-up answer is usually both. Use vector search for broad recall, cast a wide net, then use the graph for structured reasoning over what you caught. Wide recall plus deep relationships gives you fewer hallucinations and real answers at scale. The two approaches are partners, not rivals. Let me give you the phrase to carry forward. GraphRAG preserves both topological and semantic dependencies. Semantic, what things mean, which vectors already gave us. Topological, how things connect, which is the part flat retrieval threw away. Keep both, and you can finally reason over interconnected information. Here's the principle in its purest form. Some of the most important relations, parent-child, timeline order, cause and effect, live entirely outside literal semantic proximity. Two cause and effect facts can sound nothing alike. Only an explicit edge captures that link. Structure encodes what similarity physically cannot. This module is the why. The rest of the course is the how, and it's a tour of the state of the art. Construction methods, Microsoft's GraphRAG, LiteRAG, HippoRAG, LinearRAG, AgRAG, and StructRAG, and finally production multi-agent systems. Each one is a different brilliant answer to the bottleneck we just dissected. And the very next step is the most fundamental one, actually building the graph. In Module 2, we'll compare construction methodologies, triple-based knowledge graphs from open information extraction versus hierarchical community clustering, and weigh their trade-offs. Pause here, let the bottleneck sink in, and I'll see you in Module 2. Let's lock it in. The one-liner for this whole module, vector RAG stores meaning but discards structure, and graph RAG keeps both. If you remember nothing else, remember that the relationships between facts are data too, and throwing them away is the bottleneck.
If you like this video, please subscribe and share. Thank you.